So good afternoon, everyone. Minford introduced me briefly. So yes, my name is Taylor Schildgen. I'm now at the Gatset professor, but this is just since July of 2015. And before then, I was actually 7.5 years here in Gulm as a postdoc and then a group leader. So I know this department quite well. In strategy, I have a PhD student, Steffi Tofelde, and also a postdoc, Heiko Pingel. So if you don't know the two of them now, I'm sure you'll get to know them soon. They'll both be on the excursion that you'll take. All right, so for this afternoon, I'll be talking about erosion and sediment transport in the southern central Andes of northwest Argentina. So just a quick outline of my talk first. I'll give you an overview of cosmogenic nuclides, specifically with respect to measuring modern and past erosion rates. So I know that Bodo Bokhagen already has talked with you a little bit about cosmogenic nuclides and how we measure erosion rates with them. I want to focus in this talk more about comparing modern and past erosion rates. And I also want to focus on some of the complications that come about if there are landslides in the landscape. So after that little introduction to the technique, I then want to talk about what we've actually done in northwest Argentina over the past several years. And this comprises the influence of climate on erosion and sedimentation transport. And first I'll talk a little bit about the work of Sarah Savi, who's a postdoc here. And she's looking at climatic influences on modern aggradation in the Humahuaca Basin. And from there, I'll then talk about the influence of climate change on past aggradation and incision. And for this, we just go a little farther up within the same basin. Okay, so just to get started with terrestrial cosmogenic nuclides. Right, so as I'm sure you've heard, the Earth is constantly being bombarded with what we call primary cosmic rays. So these are high energy particles, mostly coming from supernova explosions, so from outside the galaxy. And when they come down and enter the Earth's atmosphere, they start to interact with molecules and produce a cascade of secondary cosmic rays. Okay, so we have this cascade of particles coming down and eventually reaching the surface. At that point, they will interact with different types of minerals to produce different kinds of cosmogenic nuclides. So these are just a few examples of different minerals, and in blue are the nuclides that might be produced. And most commonly, we're using beryllium-10, which is produced in quartz. All right, so these nuclides aren't only produced at the Earth's surface, they're also produced to a limited depth beneath the surface. All right, so essentially what's happening is these cosmic rays are able to penetrate to some depth. So if we're thinking about something like beryllium-10, which is a fairly simple system, what we tend to see is an exponential decrease in the production rate with depth. Okay, so this is just production rate versus depth below the surface. And this relationship is just shown here. So the production rate at any depth z is equal to the production rate at the surface multiplied by this negative exponential. Okay, so the terms that we have within here are the density of the material, the depth, and it's divided by the attenuation length, which is just describing how quickly that cosmic ray is being absorbed with depth. Okay. So what I'd like to do next is just take you through the history of a little quartz grain, starting off from some position several meters beneath the surface, and then coming up to the surface, moving through the river transport system and ending up in a terrace. All right? And what I want to do is stop at various points in this history and think about what we could actually do with cosmogenic nuclides in terms of understanding the processes happening. All right, so in this little plot, we have the nuclide concentration versus time. And what we're going to see is how that concentration evolves as we move through the system. Okay, so starting off, we'll have a little quartz grain several meters beneath the surface. And as it's exhumed upwards, comes close to the surface, it will eventually enter the zone where cosmogenic nuclides start to be produced. And this is typically within the top 2 to 3 meters of the surface. Okay? So at that point, we can collect a sample. All right, so this is what that would look like. We go to a bedrock outcrop, take a hammer and chisel, and just scrape off the surface. And from that sample, we would then measure the nuclide concentration. All right, so what would that tell us? All right, here we have our little rocks exhuming up toward the surface. That getting redder is indicating a higher concentration of nuclides. All right, so in general, this concentration will be inversely related to that erosion rate or this denudation rate. Okay, so to understand how that's happening, right, we started off at some depth beneath the surface with no concentration, and we eventually entered that zone where the nuclides were being produced. So if we move very quickly through that zone, we have a low concentration. If we move very slowly through that zone, we have a higher concentration. So that's just to say that the concentration is inversely related to that erosion rate. Okay, so this is the equation to actually describe how that concentration will evolve. So we have the concentration at the surface is equal to the production rate at the surface, and that's divided by, okay, there we have the erosion rate. This decay constant is for the nuclides that are not stable. We can accumulate some nuclides, and some of them will actually decay over time. The other terms we have, again, are the density and the attenuation length. Okay, so just like before. That's one possibility. Another possibility is that we don't go around the landscape and collect bedrock samples to try to estimate point erosion rates. Instead, we wait for the samples to come to the surface, be eroded, and then move into the river system, okay, where they start to go down through the river system as sand. Okay, so at that point, we could collect a sample of sand, right, and see what's happened. We've had an increase in that concentration with time. And we could use this little illustration to, again, think about what we're doing. So all these different quartz grains come to the surface. We wait for them to move down into the river system, and then we collect a sample here. Okay, so this is quite a bit different from the previous case. What we're doing in this case is we're actually, by measuring this concentration of nuclides, we get an average erosion rate across this entire basin. Okay? The equation is actually very similar to the one before. The only difference is instead of using the production rate at an individual site, we actually have to calculate the average production rate. All right? Now, an important assumption in order to convert this concentration into an average erosion rate is that we're actually contributing quartz from every portion of this basin in equal quantities. Okay? So what we have is something called a steady state denudation of the landscape, right? Everything is equally contributing quartz, right? So that would involve essentially stripping off the landscape in very thin pieces evenly, right? In many cases, if we go to mountainous landscapes, particularly ones that are tectonically active, that's not how erosion works, right? A lot of times we have mass movements, things like landslides, and this little figure is illustrating how a landslide might affect this process. So when we have a landslide, we're essentially excavating material that has a much lower concentration of nuclides compared to the surface, right? If this landslide is digging down 5 meters depth, it'll reach a point where there are essentially no nuclides. Okay, so from that landslide, we get a pulse of material that has an extremely low concentration. And if we mix that together with the rest of the sand, it will bias our denudation rates. Okay, so who can tell me, is this going to give us a rate that is too low or too fast if we mix in landslide material? Yeah, exactly. Right? So we're mixing in material with a very low concentration, which, in our interpretation would mean really fast erosion. And in fact, it was just a point source of low concentration material. Okay? We'll come back to this point later, but it's a very important assumption for this technique, that we don't have that kind of process happening, right? All right, so that's one possibility, to collect a sample of sand. Another possibility is that you have a situation where the river might be aggrading. Okay, so it's actually building up sediment in its bed over time, and then something might change, the river switches to incision. So what we do is we produce a terrace. Okay, so here we have a little fill terrace. And of course, some of the quartz grains are going to end up several meters beneath the surface. Other quartz grains will end up on the surface. And if we think about what will happen with time, the concentration, how it will evolve, will depend on that position. Right? So if we have a quartz grain several meters beneath the surface, the concentration will increase very slowly with time because we have a low production rate down there. If instead we have a sample near the surface, the concentration will increase very quickly. All right? And depending on the depth, that will dictate how quickly we are accumulating nuclides. All right, so why might it be useful to then collect samples from a terrace? Well, we might actually be able to determine the age of that terrace. So here, what we have is a beautiful pit that's dug within this terrace. This is in Northwest Argentina. It's actually a pit that was dug to create a toilet. So fortunately, we got there before it went into use. So what we could do in this case is try to determine when this terrace was created. All right, so in many cases, if we want to determine the age of a landform, a boulder that's been put down, a fluvial terrace that's been created, we could calculate the exposure age of that landform by measuring the concentration of the nuclides that are in that landform surface and dividing by the production rate. Okay, so what we have, right, the concentration, that would be atoms per gram. If we divide that by the production rate, which is atoms per gram per year, what we end up with is the unit of years. Okay, so that tells us how long has that surface been exposed to these cosmic rays. All right, very simple. That's what we call an exposure age. So how would we do this for a terrace? Well, what we'd like to do is just collect a sample from the surface, divide it by the production rate, and get an age. But that would actually be wrong, okay? Because the problem with a terrace is, if we think about it, let's just go back one slide, actually. We didn't start with a 0 concentration when all those sediments were deposited, right? Each of those little grains had this whole history that allowed them to accumulate some concentration at the time of deposition, right? So we're starting with a non-zero concentration. So if we want to calculate the exposure age of this terrace, we need to subtract that amount that we started with. Okay, so I'll just tell you, we call that starting concentration the inherited concentration. Now this is illustrating a pretty ideal situation in which the inherited concentration we assume is constant. Okay, and we could think about, what does that imply? It means that at the time that the river was aggrading, that it was building up sediment, you essentially had a constant erosion rate across your basin, right? Constant, smooth, steady erosion rate. So all the sediment that's being deposited has the same concentration, right? That prior history is all the same, all right? That might not be true. But in a simple case, that's what we would assume, all right? So if we want to calculate the age of that terrace, typical approach people use is to collect a depth profile. So going into this pit, we collect material from different horizons. We measure the concentration, and then we fit an exponential curve. And this exponential curve won't go down to 0, but it will go down to the inherited concentration. All right, so once we're able to quantify that, what we can do is subtract that inherited concentration from the surface concentration, divide by the production rate, and then we get the age of the terrace. All right, so this might be useful. Getting the ages of terraces might help you learn about the incision rate of the system over time. And in this case, if that's all you're interested in, this inherited concentration is really annoying, right? It means you need to collect a lot of samples, do a lot of analyses, and yeah, not the nicest thing. But if we think about it, that inherited concentration is actually quite interesting, right? Because essentially what it's telling us is the erosion rate at the time that that fill terrace was aggrading. Okay? So if we were to collect this depth profile, we determine an age of our terrace that's 20,000 years old. We can also convert that inherited concentration into a paleo-erosion rate. All right? So that would tell us 20,000 years ago, this basin was eroding at a given rate, which might be different from what it is today. Okay? That could be interesting if this terrace were created as a result of a change in climate or any number of things. Okay, so now imagine the case where you don't have just one terrace, but you actually have a whole series of terraces. Okay, such as here. This is along the West Meuse Valley in the Netherlands. And what was done in this study by Miriam Schaller et al. Is they first had dates for all these different terraces. They went back to almost 1.3 million years ago. Then from each of those terraces, they collected a sample, determined that inherited concentration, and then they come up with an evolution of erosion rates through time. Okay, so you could see it's quite a lot of scatter. Nonetheless, what they see is this increase in erosion rates, which then may relate to changes in climate or some tectonic forcing. But it's really an excellent way to try to quantify these changes in erosion rates. So if you think about it, we're not really limited to fluvial terraces if we want to use cosmogenic nuclides in this way. We can actually go to any sedimentary archive and potentially do the same thing. So here's an example from the Tian Shan, where they had a section that was dated with paleomagnetic stratigraphy. And in this case, it was going back to 9 million years ago. And from that section, they took samples, measured the inherited concentration, and then converted them into an erosion rate. All right, so what you see is through time, there's some variation, but overall the erosion rates are relatively low, and then we get this big spike before it drops back down again. And one of the main stories that these authors were putting forward is that, hey, we have this big spike in erosion rates right at the onset of the Quaternary glaciation, so we see a nice feedback between the change in climate and the response of the system. Okay? Any questions? was a fast overview of a number of different potential applications. But what I want to do now is focus on just a subset of those. And specifically getting into the work that we've done in the past several years in Northwest Argentina, thinking about the influence of climate on erosion and sediment transport. And this is really focused on the Humahuaca Basin, which will be one of the sites that you go through on the field trip. I think the most beautiful place you'll visit, so I hope this will also inspire you a little bit. And I've listed the number of people who have been most strongly involved in the work that I'll be presenting for the next several slides. Okay, so first of all, the motivation for this work that we started down there. Just to briefly summarize, so we know that global warming is going to affect temperature patterns around the world, but the other thing that it will very strongly affect are global precipitation patterns. Right? So this little figure is just showing the expected changes in yearly precipitation over the next 100 years. Okay, so all the areas that are colored blue to purple are supposed to get wetter, and the areas orange to red are supposed to get drier. Okay, and if you look at the scale bar down below, you can see that many parts of the world, this change is going to be more than 20%. All right. The other thing is that there should be, almost throughout the world, an increase in the intensity of that rainfall. And that just means that the precipitation that's falling is going to be concentrated into more storms. Right? So everything that you see colored green to purple is supposed to experience an increase in intensity, and there are very few places you can find that are expected to see a decrease in that intensity of rainfall. Okay, so in some parts of the world, these changes seem to be already happening, and they're affecting patterns of erosion and sediment transport. So these pictures are all taken from the Humahuaca Basin. The picture up above is of the Rio Grande River. This is the trunk stream flowing through that basin. And in this area, there's been aggradation. It's not precisely quantified, but it's somewhere on the order of 3 to 4 meters of aggradation. Right? The entire place is filling up with sediment just in the past 20 years. Okay? And that's led to major problems in terms of maintaining the infrastructure in this area. And it's the reason they actually abandoned the train line that's going up through the valley. The train tracks are essentially getting buried in sediment. Right? Interestingly, if you look at some of the tributary valleys, you can see the opposite happening. So this is one tributary going to the main stem, which has actually experienced about 7 meters of incision also over the last 20 years. Right? So they're really drastic changes. Right? And it's not just filling up, it's filling up in some places and sizing in other places. And also in the same area, if we look at the hill slopes, what we see are these very deep gullies that are carved into what otherwise looks like a relatively diffusive slope. Okay, so something has changed recently here. Okay, so just before I go back to this, so one of the major problems is that no one really knows exactly why this is happening, and it reflects 2 different types of limitations in our knowledge. The first is just a basic understanding of how will a shift in climate actually affect erosion and sediment transport on a very localized scale. The second limitation we have is what has actually happened in this region over the last 20 years. Right? We don't have that many weather stations high up in the mountains where you have potentially very local weather patterns. So actually finding a record to try to explain what's happening is quite difficult. But if we're interested in trying to better understand this problem, how will a change in climate affect erosion and sediment transport? It's a really complicated problem, and I want to give you just one example of a complication. And this example is coming from a landscape evolution model, and I just want you to focus on this upper plot first. So what we're looking at is denudation rate, and we're moving forward in model time to the right. Okay, so this model is being driven by a sinusoidal change in precipitation. And what you see is that with the first increase in precipitation, there's a major spike in the denudation rates, but the later increases, the same magnitude, result in a much smaller response in the system. Okay. Now, the reason for that is illustrated below. Okay, so in this model, we're actually starting off with relatively thick soils. So initially, there's a lot of material available that can easily be mobilized and move downhill. However, once that soil becomes thinner, we can have the same change in climate, but a much smaller sedimentary response to that shift in climate. All right, so this is one of the fundamental problems, is that the actual sedimentary response that we see can be very strongly dependent on the starting conditions of the system. All right, and these starting conditions will include things like the thickness of the soil. It can include vegetation type, the vegetation thickness and patterns, and potentially also lithology. I'm sure we could come up with other factors as well. right? But it's not simply the case that we could just go to a sedimentary archive and convert that back into a change in climate. It's a very, very complex problem. Okay, but let's say we're still interested in trying to answer it, right? What are different approaches we can take? So Sarah Savi is a postdoc in our department, and she decided to try to focus on what is controlling aggradation in the system today, right? So let's just focus on the modern system. And interestingly enough, within the Humahuaca Basin, there's one very strange tributary valley called the Del Medio, and it has what looks to be an actively aggrading alluvial fan, right? It's a really big fan. And we don't see anything like this anywhere else in the valley. Okay, if we go farther upstream, there are some terraces that you could see, but the rivers that are flowing through aren't aggrading on this scale. Also, if we go downstream, we don't see anything like this. Right? So the question is, what is happening here? What is actually causing that massive aggradation? So one of the first things Sarah wanted to do is actually confirm that this is an actively aggrading fan. Right? So another possibility would have been, okay, this is a feature that was produced 10,000 years ago and it's just sitting there. Right? So first we need to see that it actually is an active fan. So before we get to that, I just want to show you some field pictures of the fan. And essentially what it is a giant fan made up of different debris flows. Okay, so debris flows tend to have a type of sorting of the grains that are being moved downhill. So the biggest boulders get pushed to the side and to the front of the flow, and in the center we have finer grains. So you essentially get these little lobes of boulders on the surface that are marking individual flows. So here you can see marked in these dashed lines are the toes of two separate flows that are flowing from left to right across the fan surface. In this one, what we're looking at is we're sort of looking back, right, at the toe of the fan. This debris flow would have been coming at us. And here you can see down below the size of some of these boulders that are being transported. They're huge, all right? So what Sarah wanted to do is just go around, select a number of these different boulders from different debris flow units, and determine their age using cosmogenic nuclides, right? So here's Steffi with a hammer and chisel, scraping off the top part of that boulder, usually the top 2 to 3 centimeters. They measure the concentration, divide it by the production rate, and they get the age of that boulder, right? And it's the exposure rate. So how long has that boulder been sitting there exposed to the surface? All right, so here are the results, and what I want you to do is just focus on the numbers that are colored, okay, because these are showing the ages of boulders that Sarah dated, and the units are years, okay? So the youngest boulder that I was able to find is this one, 50 plus or minus 8 years. And the oldest boulder is 344 plus or minus 36 years. And what's impressive is if you look at the distribution of these boulders, they're the triangles. They're really covering the whole fan surface. So when we got this data, we were really scared because this is a pretty big fan. You know, note the scale here. So when you're hiking up and down, you know, it's a long way to walk. And we kept thinking, oh, why don't we just bring a tent and camp on the fan? We'll save a lot of time. And then we got the age of the boulders. We're like, this is probably not a good idea. The sad thing is that there are actually a number of houses that are built on this fan. And it's scary because it really is an extremely hazardous area. So anyway, what we learned about this is that it is indeed an active fan, very active. All right? And the advantage of that is it means we can start to compare the location of this fan to, for example, modern climate conditions and see, all right, can we explain the aggradation in terms of what's happening with climate today? We don't have to worry about looking at paleoclimate records. All right, so if we zoom out a little bit, what do we see in terms of the climate of this area? This is the Del Medio catchment. Here's the fan. Right? So if we go upstream, what you notice is the colors become more orange, so the vegetation is more sparse as we go upstream. As we go downstream, it's getting much darker and greener, so it's probably getting wetter. Right? So we can look at that transition in precipitation a little more precisely with a swath profile. So this is a swath profile that Sarah created just going up the valley like this. Okay, so within that swath, she's then extracting the maximum elevations, the mean elevations, and then the minimum elevations, which are essentially representing the Rio Grande. Okay? And the Del Medio catchment is marking this big nick point within that river system. Okay, so now let's compare it to precipitation, which is going across the same swath. All right, and what we see is that if we go into this zone, right? Farther in the south, precipitation is up to nearly 1 meter per year. Okay, so this is what we would call subhumid conditions. And it very sharply drops across this zone down to about 200 to 400 millimeters per year. So essentially semi-arid conditions. Right? So we really have quite a sharp climatic gradient essentially in this zone right here, going across the fan. So even anecdotally, it was quite interesting. We worked in this area for a few weeks. Sarah and Steffi were working on the fan. I was working with a student just up here. And every day, the student and I up here would come back with, sunburn. Oh, we're so hot, we're tired. Steffi and Sarah would come back, oh, we're cold, because they were in the clouds all day, and we were in the sun all day. And this is literally a few kilometers difference. So it was really remarkable what a strong difference you get over such a short space. All right, so that's one possibility, that this climatic gradient is somehow controlling this aggradation. But let's think about other possibilities. Could there be something in the geology or tectonics that's controlling that? So let's look briefly at this geology map on the left. Here again is the Dalmatio catchment. The light green in this map are showing Precambrian phyllites, and the pink are showing quartzites. All right, so there's certainly some differences as you go from north to south, but there's nothing that really jumps out as being special about that catchment. Right? Nothing that would suggest, okay, we have a massive amount of sediment coming down and it's going to build up. So let's look in more detail. Here, Sarah has mapped out the modern deposits that we see. Okay, so if we just look at these yellow colors, we could see it very limited here and here. We get to Dalmatio and it's huge. And again, quite limited as we go downstream. All right? And these are just focusing on the tributary valleys. Things change as we get out here into the foreland area. All right, so that's strange. The other thing I'll point out is that in orange are the terraces that you saw briefly in that Google Earth image. Right? So interestingly enough, when we go upstream, it looks like sometime in the past there was a period of aggradation, right? But not today. All right, so how has Sarah explained this? Well, in essence, what she's saying is that this climatic gradient is somehow leading to a change in the balance between sediment supply from the hill slopes and the ability of rivers to export that sediment from the tributaries. So let's just think about that for the southern part of this area. This is an area with very high precipitation and a lot of landslides. Okay, very active landslides in this region. So there's a lot of sediment coming down from the hill slopes, but because there's so much rain, the rivers actually have the ability to transport all that sediment out. Okay, so we end up with no accumulation within the tributary. If we go farther up, we have a different climatic setting, not nearly as many landslides, right? So we have much less active hill slope processes. So even though there's not much rainfall, the rain that is falling is able to transport that sediment downstream. So again, we don't get accumulation of sediment in the tributary. The only difference is in Dalmatio. Okay, so somehow there, we're getting a lot of landslides with limited enough precipitation that we start to build up all that sediment. Okay, so exactly why we get that misbalance, that imbalance, we can debate about. Nonetheless, it seems to be occurring at that climatic transition. And what Sarah suggested is that perhaps in order to create these terraces upstream, the position of that climatic transition shifted upwards. Okay, so there's something about a more transitional climatic zone that is leading to this imbalance between the sediment supply from the hill slopes and the ability of the river to transport. And this could be a modern analog for what we see farther upstream. Okay, so that would be the next hypothesis to test. All right. Are there questions about Sarah's study? Okay, good. So in that case, we will move on to the terraces upstream. Okay, so I've mentioned fill terraces a couple times before. Just give you a very brief explanation of what's happening. So typically we have periods of incision alternating with periods of aggradation within a river system, right? So we just switch back and forth from one mode to the other. Exactly why is not always clear. Nonetheless, if we have these shifts between aggradation and incision, we will create filled terraces, right? So these little packets of sediment that could be preserved along the sides of a river system. So in many parts of the world, these filled terraces and this change between aggradation and incision have been linked to changes in climate. All right. So also along the lines of changes in climate and how does this affect the landscape, one of the big questions that's been asked in the Central Andes is whether or not more landslides have occurred during past wetter climate periods. Right? So from the northwest Argentine Andes, there are a number of very large dated landslide deposits that have been correlated with past wetter periods. But there's also a recent Nature Geoscience paper in which they found there is no increase in the number of landslides during a past wet period in Peru, and instead the landslides are primarily seismically triggered. Right? So looking at the terraces, we're also going to think about this question of, are we getting more landslides during these wetter climate periods? Okay, so there are a few locations in the Central Andes where fill terraces have been very well dated using either optically stimulated luminescence or carbon-14 dating. So both of these are telling us about the timing of aggradation. So this is different from the cosmogenic nuclides, which would tell us the time of exposure of that terrace surface, right? So we're specifically looking at the timing of aggradation. There's also one site in the eastern Central Andes, of course, the Humahuaca Basin, where we have quite a bit of data on the timing of aggradation. And I'm just showing those locations with respect to topography on the left and yearly rainfall on the right. So in the next slide, I'm just going to show you a compilation of all these ages for the timing of aggradation. So what I did is I lumped together all the sites in the Western Andes. And what you see, this is just a PDF of the ages. So there's a big spike in the occurrence of ages that are around Holocene. Okay? That's been associated with ENSO activity. And there are also some earlier peaks in ages. Okay? If, in contrast, we plot the data from the Humahuaca Basin, what we see is this broad distribution of ages, right? And it doesn't seem to be any clear clusters of when we had aggradation happening, right? It's just happening all the time. But as it turns out, there's a very distinct spatial grouping to the ages in the Humahuaca Basin. I'll just show you those next. Okay, so first of all, if we just look at the western side of the Humahuaca Basin, that's shown in blue, we get these two spikes in ages that are correlating with spikes from the Western Andes. Okay? In contrast, if we look at the eastern side of the Humahuaca Basin, we're getting these peaks in ages that seem to be antiphased with respect to the others. Okay, and this is quite strange. This is not a big basin. Okay? And it raises two important questions. First of all, is there actually a climate control on this timing of aggradation, right? The formation of those terraces? If there is a climate control, then why do the two sides of the valley differ? Right? We're getting one response from one side of the valley and the opposite response from the other side. So how is that possible? Okay, I'm sure you've also heard about rainfall patterns in the Central Andes. I'll just briefly review again. So during the austral winter, the intertropical convergence zone, the ITCZ, tends to be relatively far north. Okay, so we get a band of precipitation in this region. During the austral summer, we get the development of the South American monsoon system, and that tends to draw the ITCZ farther south, and it also helps create this South Atlantic convergence zone. Right? So we get much more moisture coming down into this portion of South America. And of course, I'm sure you've also heard that a lot of that moisture is also transported southwards along the South American low-level jet. Okay, so within this framework, I next want to show you some paleoclimate proxy records, and we want to look at those, compare them to those fill terrace ages to try to understand what were the climate conditions at the timing of aggradation. All right? So let's just go forward with that. So here on top, we have our fill terrace ages, right? Same little plot I showed you before. And here we have a number of different proxy records for the intensity of the South American monsoon system, South Atlantic convergence zone, and then lake conditions and lake levels in southern Bolivia. All right? So first, we're going to ignore this peak in ages, which was related to ENSO activity, and we're going to focus on the two big ones that come next. And these are from the western side of Humahuaca and also the western Andes, right? The western side of the Central Andes. All right, so what do those peaks correlate with? Well, they seem to correlate generally with an increase in the intensity of the South American monsoon system, also with the South Atlantic convergence zone. Overall, it looks like lake conditions are generally wetter or becoming wetter. And also lake levels look as if they're rising during that period. Okay, in contrast, if we look at the eastern side of the Humahuaca Basin, this seems to correlate with either decreasing or more variable intensity of the South American monsoon system in the South Atlantic convergence zone. Lake conditions overall tend to be drier or becoming drier, and also lake levels appear to be falling. Okay, so if we were to just really broadly generalize from that, we could say that the western side of the Humahuaca and the western central Andes seem to experience aggradation during increasing rainfall. Okay, in contrast, the eastern side of Humahuaca seems to experience aggradation during decreasing rainfall. All right? All right, so let's look in a little more detail at the Humahuaca Basin. Right, so here, this black line is showing the outline of that drainage basin. These little magenta colored circles are showing the location of the filled terraces. And these are essentially right at the outlets of these different tributary valleys. All of the OSL dates are shown around the edges here. And on the right, you can see a map of yearly precipitation. Okay, so if you look at this map, you might say that the western side of the basin is a little bit wetter than the eastern side, but that difference is not so dramatic, right? And what I think is more remarkable is actually the difference in morphology on either side of the basin. Okay, so we've switched to Google Earth. We're looking upstream. So here's the Andean Plateau. This is the foreland. And if you were to go into your GIS and calculate the average slopes on this side of the basin compared to that side of the basin, they're actually quite similar. However, what you see on the eastern side is that you get these little perched basins, right? These little perched sedimentary basins that are separated by much steeper slopes. Okay, so the average slope might be similar, but the distribution of slopes is quite different from one side to the other. All right, and this difference in morphology is actually structurally controlled. Right? This is actually the bedding plane of the big quartzite unit that we're looking at. Okay, so let me just show you a cross-section that Heiko made. This cross-section is going in between these two white dashed lines. Okay, so that area is basically right here. And you can see we have a whole series of structures that are causing that deformation that creates this difference in morphology. So what I want to do next is zoom in a little closer and better illustrate the difference in morphology. I'm going to start off on the eastern side. I'm going to zoom into this area. Okay, so here again you see this perched sedimentary basin. It's separated from the main valley by a very narrow bedrock gorge, and this fill terrace is being sourced from that gorge. Okay, so if we go into the field and we walk up through this fill, when we get to the gorge, this is what we see. It's actually quite a narrow gorge. If we continue upstream, then turn around and look downstream, this is what we see. Okay, so here's Andy Wickert staying on top of a very big boulder. On the upstream side of the gorge, we tend to see a very thick pile of debris flow dominated sedimentary deposits. And what you see is that they're onlapping the bedrock here. Right? So we have a giant boulder here. It's also quite common to see these big boulders within the gorge also. And this gives us the impression that maybe these big boulders are helping to dam that gorge and then cause the infilling upstream. Right? Just the impression that we get from walking around there. So if we now compare this to the western side of the valley, the other side, the morphology is quite a bit different. Right? So here we have a fill terrace, and it seems like it has a pretty uninterrupted connection to the headwaters of that catchment. Right? We don't get these really narrow bedrock gorges that the sediment has to somehow pass through. Right? So a much simpler morphology. Okay, so to try to better understand how this system has responded to these past shifts in climate, we're measuring the concentration of the cosmogenic nuclide beryllium-10, both in the modern sands and from the filled terraces. All right, so what we're going to be doing, right, is getting modern erosion rates and paleo erosion rates. And on the left, in these shaded white catchments, these are the actual places where we're studying both modern and paleo erosion rates. Okay, what about landslides? Let's think about this again. Right? What we talked about already is that if there are landslides in these catchments, they're going to mobilize material from potentially several meters beneath the surface. So we get a pulse of low concentration material, which could bias our denudation rates towards higher values. All right? The other thing to consider is that landslides are not occurring very regularly. Right? It's a very stochastic process, which means that if we were to collect samples at different points in time, we could get a lot of variability in the rates that we measure. Right? Some are going to be very strongly influenced by landslides, others not so much. All right? So we can start to come up with some beryllium-10 signatures of landslides. And that would include high and variable denudation rates. Okay? Is that point clear? Yeah. Okay, another interesting thing that people who have worked in landslide-dominated landscapes have found is that there tends to be a very strong grain size dependency in the denudation rates that they measure. And specifically what they find is that bigger grain sizes yield faster denudation rates. So for example, if you collect a bunch of pebbles from your river system, that'll give you a faster denudation rate compared to a pile of sand. And the way that's been explained is that, okay, maybe what's happening is that these landslides are preferentially mobilizing very coarse material, right? Landslides just lift everything and move it downstream, whereas if we have nice, slow, steady denudation in the landscape, maybe you're more likely mobilizing sand, all right? So if you just collect pebbles, you might preferentially source landslide material. Okay, so that would be our second signature of landslides. Grain size dependency with bigger grain sizes yielding faster rates. Okay, so let me show you what we sampled in the field. So this is what one of the tributary valleys looks like. Many of them look this way. On the left is a fill terrace that's about 70 meters thick. Within this active channel, we tend to see grains that are basically subangular to subrounded, not very well sorted. And they appear to be predominantly debris flow deposits, right, that are being remobilized by the little channel here. So we collected sand and pebbles from this area. We also collected material from the fill terraces. And in this case, we dig into the deposit and we get the material that's actually several meters beneath the surface and shielded because we're getting that inherited concentration, ideally. And again, you see material that looks quite similar to the modern channels, right? So fairly angular and roughly sorted. Okay, so we also collected some material from exposed bedrock ridges like the one you see here. And essentially this was just to try to compare to our sand samples to see if we're roughly getting the same values from bedrock samples as we are from the sand, right? So a little bit of a test of the methodology. Okay, so getting into the results, first I'm just showing results of the modern samples. All right, so what we have on the y-axis is the denudation rate or erosion rate, and they're being plotted against these different tributary valleys, okay, shown on the left. So these open purple circles are showing sand samples. The filled purple circles are pebble samples. All right, and also notice that I've grouped these samples. So everything here is from a tributary on the western side of the valley. Everything here is from the eastern side. And on the eastern side, some of these samples are from the Perch Basin and others are from the tributary outlet. Okay, and then we also have a couple trunk stream sand samples and our bedrock samples. All right, so these nicely overlap. Much better than expected. What else do we see? So if we look at all of these samples from the tributaries, one thing you might notice is that, I think except for one case, the pebbles are always yielding a faster denudation rate compared to the sand. All right, so based on what I argued before, this should tell us that there are landslides happening in the landscape. All right, these are modern samples, so the nice thing is we can just look around and see, is that true? And yes, we actually have quite a lot of evidence, not only for landslides, but other kinds of hill slope processes that are essentially digging deep, right, into the landscape, not just smooth, steady erosion. Right, so we see that with these deep gullies that are being carved. We could see that in these big slumps. And what you're seeing here is a mud flow that actually came out of the base of a landslide about 2 years ago, and it buried this restaurant. So this restaurant is right along the main road going up the Humahuaca Valley. So if you tell Heiko you want to stop there, he'll let you take pictures. Okay, so that result is not surprising, right? We're getting the pattern that we expect for a landscape that we know is experiencing landslides and other kinds of hill slope excavation. So that was just the modern samples. What I'm going to do now is add in the samples from the fill terraces. It's going to get messy, but just be patient. Okay, so in this case, these little open green squares are sand samples from the terraces, and the filled green squares are pebble samples. All right, so let's first just look at the western tributaries. All right, what we're seeing is some extremely high paleodenudation rates. Okay, this is 1 millimeter per year, so these are extremely high. And if we compare these overall to the modern samples, not only are we getting quite high rates, but they're quite variable. And there's still some evidence for grain size dependency. It was really hard to find sand from the terraces, unfortunately, but right, we still see some evidence for a difference there. So what this might be telling us is that at the time that these terraces were grading, filling up, there might have been even more landslides happening in the landscape, right, to give us that stronger signature of landslides. Okay, so remember on the western side of the valley, that would have been during times of increasing rainfall. Okay, that's the western side of the valley. Next, let's look at what's happening on the eastern side of the valley. Okay, so what you see is there are a couple paleodenudation rates from pebbles that are a little bit higher, but overall these paleodenudation rates are actually overlapping quite nicely with the modern denudation rates. There's not a very big difference there. So what that would suggest, from the same argument that I used before, is at the time that those terraces were aggrading, there were a similar number of landslides in the past compared to today. All right, so we'll just say that. And remember, on that side of the valley, the terraces were actually aggrading during times of decreasing rainfall. All right, and I would like to point out that there's one really obvious outlier. Okay, there's this one paleodenudation rate from the Perch Basin that's clearly much higher. So it might be that the Perch Basin is different, okay? So there we might actually have more landslides in the past, maybe. One sample is a little bit sketchy to try to interpret, but we'll just keep that possibility open. All right, so how can we explain this? Right? And specifically what I want to try to explain is why during times of increasing rainfall are we not creating fill terraces and more landslides on the eastern side of the valley? Right? How do we explain that? Now I think what's going on is actually a little bit simpler than that. So during times of increasing precipitation, we might have actually triggered more landslides everywhere in this landscape. Okay, but let's think about what would happen on either side of the valley. First, we have the western side of the valley with our relatively simple morphologies. So if we have landslides happening, we mobilize material and it could relatively easily move out down into the trunk stream, right? And start to build up maybe some little fill terrace. If we think about the eastern side of the valley, however, if there's a large sudden pulse of very coarse material, that could potentially dam those really narrow bedrock gorges, right? And instead cause the filling of material upstream within those little perch basins. Okay, so that little narrow constriction is basically forcing you to accumulate material here. All right, so if we then go to a period of decreasing precipitation, maybe landslide activity everywhere would be reduced. Okay, and that would potentially give us time to start to clear out those bedrock gorges. Right? Maybe slowly start to re-excavate material from the Perch Basin and then slide it down through the slot into the main valley. Okay? And that slow re-excavation and remobilization process could actually give the sediment more time to accumulate beryllium-10. Right? So even if we might have started off with a landslide signature in this Perch Basin, as we accumulate more beryllium-10, we might lose that signature as we go down to this little terrace. Right? So we lose that signature as a result of that delay in this process. Okay, so the story could be quite a bit simpler than it seemed at first, right? We might actually be seeing exactly the same landscape response to climate forcing, but exactly where the sediment is accumulating and when it moves into the main valley is being controlled by the basin geometry and something else that we call the landscape connectivity, right? So how well connected are different parts of the landscape. Okay, so that's what I just said with that point. Okay, and the idea was that during times of increasing precipitation, we do indeed get landslides everywhere, right? But on the west side, that landslide material moves out immediately. On the east side, it gets trapped. During periods of decreasing precipitation, there are fewer landslides, and that allows us to actually start to move material on the east side down into the main valley. Okay, so what might this imply? If we go to the outlet of the Humahuaca Basin and were to look at some sedimentary archive, we might wonder, okay, are we going to see some signature of these climate shifts in that sedimentary record? And the answer could be, well, maybe not, because during one climate phase, we're having sediment delivered from this side of the valley. During another climate phase, we could have sediment delivered from the other side of the valley. Right? So anytime we have a relatively large basin that's integrating subcatchments with very different geometries, we could potentially get a much more muted sedimentary response to these climate shifts. Okay? So then we could ask the question, well, is this actually important? Right? Or is the Humahuaca Basin just a very strange place that we happen to start working in? Right? Well, we can think about what is driving this process. And essentially, it's that structural deformation, right, that caused these very different geometries. Right? So if we step back and we look at the central Andes, we could think about, okay, what we have here is a huge zone of structural deformation, right, spreading across a very broad region. Right? And if that's the case, what we'd expect is to have some drainage basins that are actually integrating these different geometries, which then should drive this type of process. Right? So some basins are going to have a much more delayed sedimentary response compared to others. All right? If we were to contrast that with the western Central Andes, this is where we have basically a big monocline. Right? So the river's draining that area. If sediment is produced up here, it's not going to take so long for it to go downstream. Right? So in this area, I'd say we don't worry so much about this kind of process, but in the eastern Central Andes, this could actually be a fairly important process to think about. Okay, so just to summarize, right, in terms of our modern aggradation, right, the only location where tributary fin is aggrading is at this climatic transition between subhuman and semi-arid conditions, supporting the importance of some transitional climate regime on erosion and sediment transport. All right, so that's what we use to kind of think about what's then happening in the past. Right? Are these transitional climates also important? And it seems, for the most part, yes. Right? We saw these terraces aggrading during these changing climate conditions. We were either getting wetter or getting drier. So periods of increasing rainfall in the past appear to have driven increased hill slope erosion and river aggradation in the Humahuaca Basin, except in places where complex catchment geometries were delaying the transfer of sediments. All right, so this is another point that I'm not really going to go into detail, but I'll suggest you talk to Steffi about it. And I just wanted to point out that within the Humahuaca Basin, what we're seeing is several different periods of aggradation and incision, right? We had multiple peaks and ages. And as it turns out, these peaks and ages seem to be following roughly 20,000 year cycles. So it could be related to some precessionally driven climate forcing. All right? The crazy thing is if you go one basin to the south, the Toro Basin, which is where Steffi is doing her PhD work, she sees, instead of a whole series of terraces on 20,000 year cycles, she sees 4 or 5 main terraces that are on 100,000 year cycles. Okay, so this is one basin to the south. Instead of being sensitive to maybe precessional climate forcing, it seems to be sensitive to eccentricity forcing. Okay, and why that is, we have no idea. But this is Steffi's job to think about it. And you'll be going into the Toro Basin with her, so it'll be a great time for all of you to say, hey, Steffi, what do you think about what is causing the creation of these terraces? So I definitely recommend you talk to her about it. And you'll be going through both of these areas, so please keep the lecture in mind and keep thinking about these processes.